Okay, so today we'll try to understand NMR, which is nuclear magnetic resonance, with minimum amount of force. That means I'll use very less amount of mathematics, which normally I do, just by physical arguments. Now, to understand NMR, what I'm going to tell you is first a simple experiment in which I'll take a CD. Okay, so this CD is it's always going towards the gravitational field of Earth. Whatever I do, let's say spinning, it's spinning. It's hard to see, but it will always go towards the center of the Earth, which is due to the gravitational field of Earth. So the same analogy happens in nucleus also. When you apply a magnetic field, the nuclear magnetic moment, which is due to protons or whatever, they tend to align with the magnetic field, same like this CD is trying to align with the gravitational field. Now what happens is if you give a tilt and since they are spinning, they'll keep spinning. They will do this kind of motion. The CD will do this kind of motion. Since it is frictionless, I cannot show you, but okay, you have to believe me, it will do this kind of motion. After some time, of course, it will come to the center of the Earth again and it will start spinning. Now, but this frequency which is happening, it's called, it's precessing at some frequency, and you can see it also. It's called Larmor precession or Larmor frequency. It's named after a scientist. But to do so, what you have to do, you have to apply, you have to give a torque which will shift this plane of the CD from this vertical direction to the horizontal direction, and you have to do in such a way that this oscillating field is in the same frequency as the frequency with which it's processing. And after that, because of the angular momentum, it will start processing around the magnetic field. So that is the idea. So the same concept will apply. We have a magnetic field. We'll have a magnetic field with which nuclear spin will try to align, and we have to apply an oscillating magnetic field. It's like same as a torque which we applied in the CD. There is a special name for this oscillating. It's called 90-degree pulse, because you are applying orthogonal to the applied magnetic field. Okay, so that's what happens, and you see that's what happened in nuclear magnetic resonance. And now what I want to do two more thing is normally the signal is very weak, so to get the good signal, what people do, they normally apply magnetic field. Of course they apply magnetic field, they apply high magnetic field. Now the idea is very simple. Idea is very simple. So when you have applied, let's say these are the spins, B is equal to 1 Tesla, there will be Giemann splitting, and you'll get this, let's say spins are like this. So you have there are a number of spins in ground state and the excited state. There are not much difference. There is only one which is contributing. Only, of course, you have to have at least one spin to contribute to an agreement. Let's say I apply 5 Tesla. Now this splitting, now this distance has increased. The splitting energy. So what you have is now on the end of the day, you have large number of magnetic moments, compared to B is equal to 1 Tesla. So this is one technique. That's why you see in NMR or MRI people mentioning 3 Tesla MRI, 5 Tesla MRI. That means they are more accurate. That's all they means. One more thing you can do is you can cool down your system. Now what happened at higher temperature, everything is jumping around, so you have equal number of spin up and down. But let's say you cool it down. When you cool it down, they don't have enough energy from go to the ground state to the excited state. You have a large number of spins available. So when you have a large number of spins available, then you have a large magnetization, and detecting the signal is very easy. So idea, what you have to do in case of nuclear magnetic resonance, you have to apply magnetic field or transverse magnetic field, the same frequency as with which spins are precessing, which is also called 90-degree pulse. Thank you.